Hello everyone. I'm Yannis Tsouros. I'm a postdoc researcher in the University of the Aegean, and this training course is focused on the tactical passenger simulator, which is essentially an activity-based model developed in the context of the Harmony MS. And during this short training session, we will be able to see both a theoretical overview of the activity-based models, their uh, context and the objectives that they serve, as well as the specifics of the tactical passenger simulator within the Harmony MS. So the presentation outline is mostly an introduction, first of all, to the activity-based models, then discusses the tactical passenger simulator architecture, and then we talk about the data that we need, the multitude of data actually that we need for the tactical passenger simulator, the submodels of the simulator, the decisions that they help make, and then how the tactical passenger simulator is integrated in the context of Harmony MS. So, the questions that we will try to answer during this training course is are all revolve around why do we travel travel behavior. And the first question that we attempt to answer when modeling travel behavior is how will the transport system as a whole look 10, 20 or more years in the future. We do not have any magic or special knowledge about the future. We can only make some educated guesses, and the promise of modeling as a methodological tool or a technique is that we can predict some of the outcomes of the transport system if we change some variables, and of course we leave some variables unchanged or projected in the future. Going to the more practical implication of modeling travel behavior, we want to see what is the potential effect of policies that we investigate. For example, if we want to apply a low emission zone in the center of a city, we would like to see how this affects the congestion or the vehicles that they move within the city or the modal split. Of course, this is just an example. We will be able to, using the simulators, we are able to see how the changes in the economic, social, and built environment affect the transport system, and we can also quantify this effect using the techniques that we will describe. Another important point is to quantify the effect of the presence of new modes of transport or new infrastructure in the network. For example, we may be able to investigate how a new metro line in an urban area will change the transport network and the demand and supply for it. And also we are able to model the effect of the presence of new modes of transport that are not yet available or really popular in the market. For example, the use of autonomous vehicles. The overall chain of events would be that we use the travel models, we get quantitative results, we assess the system performance, and then we can make more informed evaluation and assessment of the policies and the situation, the scenarios of the future. In the context of the traditional simulation models, one of the most commonly used models in practice, even nowadays, it's one of the most popular methods that we use, is the four-step model, which does this four-step sequence of models starting from trip generation, which is the amount of trips that are generated in each zones. Then it does the trip distribution using most usually a gravity model. then it estimates mode choice models for the different mode choice available in the network, and then it does the network assignment. On the other hand, the activity-based model focuses more on the disaggregate demand for travel. So the trip generation analogy to the activity-based model is the activities and travel generated per agent. So the demand is generated on a disaggregate level, on an agent-based level, based on characteristics of the agents and the household. Then both the distribution and the mode choices are done in both trip and mode and tour context. So we have some more detail, and we have a chain of trips which constitutes the tour. And this way we can add more dependencies and more constraints in the mode choice and distribution models of the simulation. Of course, another big difference between the activity-based and the four-step model is the temporal dimension, where in the traditional four-step model it's mostly a daily average, maybe 2 or 3 different periods in the day, the peak hour, for example, and off-peak hour. Whereas in the activity-based model, we can have even continuous time in minutes, or different discrete ranges of time, hourly, sometimes even more aggregate as 3 hours. But in any case, we have the ability to do this even in continuous time, which adds significantly to the detail that the simulator can model the transport network. In one sentence, sourcing this to one of the big experts of activity-based models, Professor Bowman, the activity-based models focus on the individual and treats time in a continuous manner. This is the big difference from the traditional four-step models in one sentence. In the figure below in this slide, you can see the complexity and the interdependencies in the cases of tours. So the first small figure on the left is a simple tour where the agent travels from their home to their primary destination and then back home. The trips in this tour chain are indicated by 1 and 2, which are the 2 trips that constitute the tour of this agent. Even in this simple case, we can see that we are able to put some constraints, so we can make our model to be more realistic. For example, if the agent travels from their home location to their primary activity location, let's say this is the work activity, we can see that if this agent drives their car to work, they have to also use their car to go back home. They cannot leave. In most of the situations that we can predict in the model, there is no reason for the agent to leave the car at work. This constrains the mode choice model, for example. So if we estimate that this number 1 trip is done by a car as a mode, we should also conform the number 2 trip mode to be car. In the traditional four-step model, where these two trips are modeled independently, it is possible, though unlikely, to predict that these 2 trips are done by a different mode. If we use the tour-based mode choice, it is more plausible that we get a more realistic result. Of course, this is just for the simple case of a simple tour. But then we can also adjust our model to predict secondary destination in the primary tour before, as in the second figure of this image, then maybe after the primary destination. So we add interim secondary destinations within the tour, so more stops, and then the tour becomes a tour with 3 different trips. So it's home to the primary activity and then maybe a stop for shopping. And then we also have the ability to predict work-based tour. For example, the agent drives to work and then walks to a nearby location to have a lunch, and then comes back to work, again walking, and then they take their car and they go back to their home. Additionally, we can have even more complex structures of a tour. But in any case, the main meaning of this slide is that we have the ability, in the context of the activity-based models, to do more complex tours, model the travel behavior of the agents in a more realistic way with added detail. The reason we may want to use activity-based models is that the activity-based models mainly represent each person's activities, which are the main cause of the out-of-home travel. As you may already know, most of the trips done by people every day do not have the trip per se as the trip purpose. So if we ignore the trips done for a short walk or a big walk around the house, or maybe an excursion or a trip to the countryside, most of the trips are conducted because we want to participate in an activity that is in a different location than the one we are already located at. This reason, based on this, we are able to model the activities of the person, which is actually the reason we move. This is why we call travel demand for travel, an induced demand, because it is actually based on the need to perform an activity and not just because we want to travel. Also, the ABMs, as I mentioned before, consider the entire day with all the different temporal dependencies present in the daily schedules. For example, we may want to reschedule a trip, a secondary activity, if it's really temporally close to an existing activity, and not model them independently. And also, if we're running late on an activity, we may want to add the secondary stop in the same tour and not go back home and then start again. Also, the activity-based models have the ability to prioritize between activities. So maybe a shopping activity has a lower urgency than a work activity, and this is reflected in the way that the activity-based models schedule tours. Also, joint travel and intra-household dependencies and common decisions can be modeled explicitly in ABMs. All in all, they provide more detailed analysis, leading to more room for specific policy measures and less aggregation errors. This is an example of how the trips may be scheduled in the context of an activity-based model. So we may want to schedule the work trip as a first priority, because this is the activity that has the most constraints and it's the more urgent to be conducted on a daily basis. Then we have the shopping activity scheduled after this one, and then we can schedule the third activity, which is the eating out or going for a lunch, in the space, in the temporal space, in the room they live. The two activities that are already scheduled live for this one. So, going back to how complex the tours can be, it is a decision of the modeler and the developer of the simulator to decide how complex we want to be with our tours. This is just a sketch of how we can just model the trips to work and back. Maybe we want to add some dependencies, because the agent traveling to work may want also to drop off their kids to the school and then maybe pick them up, and also conduct a short lunch break and go to a nearby restaurant to have lunch. All these different trips can be modeled independently in the context of a traditional model, or they can be modeled as a single tour or as two different tours. In any case, we can go as deep as we want, but sacrificing a bit of the predictive capabilities of the model and based on the available data we got for the specific use case. So this is a very short introduction to the activity-based models. We should all keep in mind that if we want to gain a bit more knowledge into activity-based models, I'm going to leave a link on the bottom of this presentation to read an activity-based models primer, which is a really good source for introducing someone to activity-based models. And let's talk about the Harmony model suite, and more specifically for the tactical, the midterm, let's say, horizon of the Harmony MS, and even more specifically for the passenger side of the tactical simulator, which is essentially, as I mentioned before, an agent-based and activity-based model, which models passenger demand in the daily level, in daily basis. I'm not going to spend a lot of time describing this figure, but the main outtake of this one is that we were using different inputs and outputs from the different Harmony MS modules to get data from the strategic models and output data to the operational models. The core of the activity-based model is a software component we call the adaptive scheduler. This is a component written in R, which essentially applies the estimation of the parameter estimated in the models to a synthetic population, which is generated on the strategic level. And this way we can step by step, like puzzle pieces, fit together all the different activities and travel of the agents in a daily basis, and then even do adaptive scheduling of the activities and the trips in order to derive the final agent schedule, which is the main output of the tactical passenger simulator. This is an example, a sample example of what do the agent schedules look like. I have included the very first application in the context of Harmony, which has been done in the context of the Aimsun Toy City, a small area around the Camp Nou in Barcelona. And also I include some of the sample graphs that indicate the popularity of activities in the daily context. This is in the table in this slide you can see the way that the agent schedules are produced, are generated by the tactical passenger simulator. And then on the bottom side you can see the different time allocation of activities for different type of activities. Just a bit, a small insight into the data we use to estimate the models for the Turin area and for the Oxfordshire area. We can see that we have the home locations of the surveyed households and agents in Turin, and we can see that we try to have a representative sample, so more central zones with more population are represented in the sample more than outside zones. Of course, this is a sample of around 600 individuals, which is was sufficient for us to estimate the models, but of course it does not cover every zone in the study area in Turin. I'm going to skip these two more technical slides and jump into the data, which is an essential and a very important part of preparing our models. And in this section, I'm going to try to introduce you a bit in the necessary data that we need to fit the model in order to have good estimations and a good application of the simulator. It is a major issue most of the times because the activity-based models are data hungry, meaning that there is need for extensive datasets which are commonly not available for the study area. The main datasets that we need to estimate an activity-based models are detailed activity and travel diaries, which are kind of difficult to get. In European cities, it's not easy to have existing activity or travel diaries. There may be some sources that have time use data or some existing travel diaries from previous surveys, but most of the times this would require a detailed activity and travel diary data collection. In the context of the Harmony project, we had planned and designed to do a data collection using the Mobi app from the project partner Mobi, which essentially does exactly what we need for the activity-based model. It provides an app, a mobile phone app to the survey participant, and this app automatically logs the activity and travel of each individual on a daily basis, needing some, of course, validation on the side of the user. But it eases the burden a lot. It's much easier to do this type of data collection, and in the Harmony project, it has produced an important input for our models and has streamlined the work in a way that it was easier to conduct the data analysis and preparation than previous studies or using existing secondary or primary data. Another important data set that we need is the data from SP experiments. Stated preference experiments are experiments presented to users where they are supposed to answer to different tasks with choice cards, to represent a future scenario or a situation that is not currently available in their area. For example, an example of a stated preference experiment would be a mode choice experiment between existing modes and also future modes. For example, in the Harmony project, we had this SP experiment where we presented the users with different mode choice options, some of which included autonomous vehicles, flying taxis, or different integrated ride-hailing services that were not currently available to their cities. As I mentioned, the solution for this multitude of data needed for the models was to use the Mobi app in the Harmony project. So we collected digital travel and activity diaries and the answers to the responses to the SP experiments. There is a need for agile development in each study area. In essence, we want to do a correct, fast, representative data collection, and of course, doing this and also doing a cheap data collection is impossible. So one of these parameters should be, minimized. In Harmony, we chose to be very careful in data collection, and this led to an estimation of the models as we planned in the context of the tactical passenger simulator for both Turin and Oxfordshire. The types of data that we require for the activity-based model can be split into two main categories. The one is the aggregate data, which is mostly available from secondary sources. We use the census data, and we prefer to have a detailed geographic distribution where available. And also we use land use and land use transport interaction data from the LUTI model. We also use regional economic model to get data regarding the variables used in the model, and also the demographic forecasting model to have the future projections for key variables that are useful for the estimation of our models. On the disaggregate side, as I mentioned, we use the activity and travel diaries, mention some ways to get them, the stated preference experiments, and also household and individual surveys that are very useful as they are the source of some of the key variables estimated in our models. To do these household surveys, we also use the Mobi app, and we presented the users with questionnaires, digital questionnaires, where we ask the general sociodemographic questions that you all, I'm pretty sure you all know this type of questions. Some travel behavior, habitual travel behavior questions based on the frequency that they use some modes, the preference, any challenges that they face with the existing modes, etc. And then we also included attitudinal questions, psychometric, perceptual questions regarding different various themes and topics. For example, we used some COVID-19 related questions because the surveys were conducted within the pandemic period and a bit after that. We also discussed satisfaction with existing modes and services and other transportation specific questions. The activity and travel diaries now form an immense amount of data. For example, in this slide, I show you I can show you the amount the immense amount of road GPS traces that we gathered. This is a busy junction in the center of Turin, and each small dot that you see in this image represents a location of that was logged in the travel survey in Turin. And if I go a bit downstream, you can see that if I aggregate the hourly GPS traces in this busy junction, you can see that for each hour we have outlined paths of people going in and out. This is for the first week of April, and if the aggregation is done in a daily basis, you can see that we have extensive coverage of the locations around this junction, and most of the times it outlines all the roads and the streets that are located in this area. This is just an example to show you the richness of data that we get out of the GPS-based survey that we did in Harmony in order to get the travel and activity diaries. Going forward, we just as a small representation in the format of a map of the land use and network data that we use in Harmony. For example, the number of schools, hospitals, and universities. Also, the zones and the road network are, of course, important and critical input points. And this is an example of the stated preference experiments that we used in the data collection process for both cities that were involved in the deployment of the tactical passenger simulator. The first screen on the left of the slide shows the remote work experiment, where the respondent was presented with the decision of going from fully remote to fully office as a work setting, with the different attributes of this decision being the wage adjustment and the working hours adjustment. Of course, we had a preliminary screen where the user could respond whether the change of the work setting is a realistic situation based on the work they do, because we're well aware, as you are, I guess, that some of the work conditions cannot be changed to remote work, of course, and more importantly, it is not always the decision of the employee or the worker to change their working condition to remote. So we asked them to do this experiment as if they were the sole decision makers for this decision, but then we weighted the responses based on how realistic this assumption is in reality. The second screen on the right of this slide is the mode choice experiment that I mentioned before, which presents the user with a decision of mode choice in the context of their most popular activity in the day, which is data derived from the Mobi app, and this is also an important integration in the form of data collection, that we were able to do realistic predictions of the activities and the trips and present a sample of these trips as a realistic situation to the user. So the user had to choose between 6 different modes: shared vehicle, walking, cycling, using the public transport, using their private vehicle, and ride-hailing options. And the travel times were adjusted to the actual travel times that the user has reported or the app has captured in their daily travel. Of course, this is the place where, as I mentioned before, we include also different levels of autonomy for some of the options. and in some cases even futuristic modes as flying taxis in the context of this experiment. An important part then on the developing of the model is the data handling and the streamlining of data. The data collected through the Mobi app, which is already solving the issue of digitization of the travel and activity diaries, still needs a lot of post-processing, which some of which is done in an automatic way, and another part is done based on the knowledge and the experience of the data handler. So there are some algorithms which automatically clean data to remove GPS error and aggregate activities, but then we also need to input predictive algorithms and to do some manual tasks in order to create the exact format of data that is supposed to be the basis for the modeling activities. In a nutshell, we can say that there are three different components in the streamlining of data from the Mobi app to the activity-based model. The first is the automatic creation of the activity and travel diaries done automatically from the app. Then there is the module which does the data handling and cleaning of the data and also prepares the data to be put into the final format. And then there is some pre-processing algorithms and automatic handlers which put the data in the exact correct format that the activity-based model, the tactical passenger simulator, needs in order to start the process of estimating and applying the models. Now, talking about the models, we're jumping into the submodels section of the presentation. And this is the place where we discuss the engine of the tactical passenger simulator, which are the models and the submodels which aim to model travel and activity behavior. Each model is focused on a single puzzle piece, as we like to call the different components in the tactical passenger simulator. But some of the models are interrelated, some in a pretty straightforward way, as you can see, as you will be able to see in a bit, and then some are related in a more complex way. To see which models we need to predict an agent's behavior, we will start by a simple example. The example that I will present in a bit is not the exact sequence of models used in the final version of the tactical passenger simulator, but I think it's a good start for someone who is interested in activity-based models to see the overall workflow and how we treat the different activities and travel puzzle pieces, and how we can start organizing the sequence of estimating the models and applying the models to schedule the whole day of an agent. So if we put ourselves in the position of considering the decisions we make during our morning routine, the decisions we take before conducting our first out-of-home activity can be split into decisions that are made in the past and are kind of strategic decisions. For example, the current work situation that we're in, or the work location, for if we want to speak in spatial terms, and also some shorter term decisions such as what mode will I use to get to work. Of course, the decision of what mode do I use is also based on strategic decisions. For example, if I have decided in the past year to purchase a private vehicle, this vehicle is now available to get me to work. If I hadn't done this decision, there is no private vehicle available in the household. So I have a restricted, let's say, choice set of mode choice for my daily travel. And of course, it's not always clear what degree of freedom does the individual have. The way that we model this decision is based on the existing literature, of course, and very significant contributions that have already outlined the different ways we can do this. But in this example, I'm going to keep it simple and just to let you know and to introduce you into how we treat this sequence of decisions. So if we want to start thinking about the models in very generic and simple questions, a sequence of 5 questions can be the leading way that we decide to sequence also the models we're going to estimate and to create some dependencies among each other. So if the first question is do I go to work today, the truth is that even from the collected diaries and the available literature, it's obvious that not all workers go to work every day. There's a million reasons why they don't go, but a model shouldn't assume that every worker goes to work. In the context of the tactical passenger simulator, there are 2 main models that predict this decision. But there is also an updated use case where also people are allocated in the future a remote work percentage. So there is a probability of people working remotely based on different factors. The second question is, what time should I be there? Which is the main temporal constraint. And this is what essentially dictates the time that I want to leave from home. Because if my work starts at 9 a.m. sharp, it is not possible to be flexible on the work start time. This is why we model the work start time and not the departure from home time, even if other models are more prone into modeling other type of temporal constraints. Then I have to ask myself, do I have to do anything else before? As an out-of-home activity. And a very frequent secondary activity before work is to drop off kids or other household members at their own activities. And then there's a decision of where do I go today? Of course, it's obvious that for most of the work settings, out-of-home work settings, the work environment is located in the same place each day. For a part of them, it's not that obvious. In any case, this is the place where we want to put the destination choice model, where we will be able to predict where this agent goes for work. The final question is, what mode do I use to get there? So based on the choices that I have available, which is the mode that I choose to go to work each day. Some of you may think that some of these decisions are based on a more strategic level, and during the habitual travel schedules of each specific person, the destination of work or the usual mode that I have to go to work is a decision that does not change from day to day. In any case, of course, this is correct, but the way we predict and estimate the models cannot be based on this type of habitual knowledge, because we do not have the knowledge, of course, for all the persons in a city. So, to get a bit more practical in terms of which models are employed to give answers to these questions, for the first question, there is a small model that predicts the decision to go to work. And also there is a more sophisticated model, which is a activity participation and duration model, which essentially predicts the probability of a single agent to participating in all types of activities, including work, and also the duration of this activity. Another model that is used in the context of answering this question is, as I mentioned before, the remote work model, mostly used for future applications, where we also have some interesting results regarding the percentage of people that are willing and can work remotely. After this models are estimated and we get the parameters, we can create the first tour of the day, which is the home-based work tour. Based on some data from Turing, we can see that most of the people conduct a single work daily episode. Some of them also have a second daily episode. And the percentage of people that have 3 or more work episodes in a day is very small. The same is true for the education daily episodes. Almost 95% of the students in the sample conduct a single educational episode in the day. Then we move away from the answer to do I go to work today by considering what time should I be there. And then we have the duration of the work, which is derived from the activity participation and duration model, the MDCEV model that I mentioned just before. And this way we know the duration of the work activity. And actually this is the first time where we can see a clear dependency between the outcome of a model and the input for another model. So the work start time model, which is actually a regression model for both Turing and Oxfordshire use cases, uses as an independent variable the work duration predicted in the previous model. So in order to have a good performing model for the start time, we need the outcome from the previous model. And this is what essentially demonstrates, for the purposes of this training session, the dependency between two models. And this is important to note because there are different ways to communicate results, outcomes of one model to another, and this is the simplest way of doing this. Getting a parameter estimate from a previous model, applying to the synthetic population, and then predicting the new model as with the input that we need. Of course, in the context of estimating the models, this is done using the travel and activity diaries derived from the Mobi app. And of course, we know at the same time both the duration of the work activity for the estimation of the models and the start time of work. The application that I mentioned happens on the backend, on the adaptive scheduler, where the duration which is applied in the duration that we get when we apply the estimation of the first model to the SNP population, it becomes then the input for the application of the second model. And this leads to this kind of backend transformations that I've been talking about in this slide, which essentially are arranging the work start time and arranging the work end time based on the work duration. This is the most, let's say, complex part of scheduling, the actual scheduling of activity start times and end times. And this happens in a dynamic way in the context of the tactical passenger simulator, and I will come back to this in a following slide. We have the mean full-time employment, part-time employment, also self-employment and part-time self-employment, work start times. In Turing, they were a bit later than the actual observed times. In Oxfordshire, they were mostly on time with the reported data. And we observed that this kind of shift can be attributed to sample differences, and also maybe in the big percentage of remote workers we had in the Oxfordshire, in the Turing case, excuse me, because the survey was conducted during the pandemic. And as a small theory break, I wanted to introduce that based on the simple discussion, the simple dependencies that we discussed in this slide, there is a big discussion on which of the following should be modeled first in the context of an activity-based model. And the truth is that a lot of researchers and practitioners of activity-based models have proposed different sequences of generation, time of day, destination, and mode choice models. The truth is that you should make an informed decision based on the literature, based on the availability of data, and based on the specific use cases that your model wants to investigate and to explore. There is no consensus on which is the best sequence, and my opinion is that the modeler should be flexible on choosing the sequence based on their actual needs and based on the theory that comes with the total and integrated understanding of the use case and the specific particularities that come with the needs of exploring and assessing the use cases. Then we jump to the do I have to do anything else before, which engages the joint decision models of the tactical passenger simulator, dropping off another household member. And this starts to add to the complexity of the scheduled tours by adding stops before the main primary stop of the tour, which is the work activity. And what this essentially does on the back end, on the adaptive scheduler, is that it modifies the home-based work tour to add a secondary stop before. It should be noted that for each different trip and tour first and trip then scheduled, the adaptive scheduler, the backend, the software module of the tactical passenger simulator, initiates a chain of future events, which is the estimation of the destination and the mode choice for each one of these trips generated. So we want to be we want to include detail in our models, but we should also keep in mind that detail and computational time and processing are two variables that cannot be optimized at the same time. So if we add to complexity, we may gain in detail, but we lose in terms of computational operations and time that the model takes to run the whole simulator. And also we add a bit to the complexity in terms that we cannot be really sure how rigid are the results that we're getting. The actual outcome of the surveys for both Turin and Oxfordshire indicate that most of the tours are simple tours, 42%, but of course 21% of the tours have a before work stop, 28% of the tours have an after work stop, and then we have both before and after in 9% of the tours. Of course, this is an indication that we cannot have a realistic model if we just model simple tours. So we should include the different before and after stops in the tour structure, and we should accommodate the development of models which do this. Of course, it should be noted that the before and after work stops are not only joint drop-off, pick-up tours. There are also secondary activities such as eating out or social activities, shopping that happen before or after work. Then we can addressing the where do I go today for the work activity. We have the option to choose between engaging longer-term decision models and stored usual work locations, or maybe some shorter-term decision as if we want to model people, and we saw in the previous chart that 15% of people have multiple work episodes, and maybe these are also not only temporally different, but also spatially different work locations. In any case, this is the place where we engage a destination choice model, and this is a model that predicts the zone that the work activity will happen for each individual. And in the context of the tactical passenger simulator, this model uses mostly accessibility data, land use data, distance, travel times from zone to zone, in order to predict where the work location and also other type of secondary activity locations will be based on the zone that the individual is currently located. And we can see that for a big percentage of shopping or joint trips, we have maybe for a third of them, we have the trips happening on the same zone. So the destination choice model also accommodates for this specific option where the zone can be the same zone that as the origin. The destination zone is essentially the same as the origin zone. Of course, the chart also shows that for work and education, this is mostly not true. So 85% of the work and education trips happen outside the origin zone. And the final model that we initiate in order to complete this simple example is the what mode do I use to get there. And here we use the RP model. The model estimated using revealed preference data, essentially the data from the Mobi app, the travel diaries of the Mobi app. And then we allocate the travel mode to work. After we estimate the model, we apply it to the snake population we have. For the specific trip to work, what mode did the agent choose to travel? In most cases, as I mentioned before, the adaptive scheduler also conforms the return to home mode to be the same. And I'm going to leave this as an open question, whether you can think of any exceptions to this rule. We have included some exceptions in the context of the tactical passenger simulator, and I'm going to leave a short link with the exercise and answers to these kind of questions in the end of the presentation. This is the adaptive scheduler flowchart, and I'm not going to bother you with the particularities of this flowchart. I know that this is a complex image to follow, but the truth is that this kind of describes the different workflows of the tactical passenger simulator based on different parameters and specifications that are either done by results of the models or by user specification, as we will see in a bit. So, for example, if we have a worker that is supposed to work remotely for this daily schedules that we predict for this specific day, we skip entirely the work-based tour, the home-based work tour, and we go to schedule the secondary activity of the day. After, if we skip the work-based tour, we already skip a big part of the scheduling process, and we jump to the secondary tour, which initiates another sequence of scheduling and estimating and applying models. If the agent, though, is not supposed to work remotely, then we and also predicted to participate in a work activity, we start the regular scheduling of the first tour of the day, which is the home-based work. And then we have different specifications where, of course, we can see if there's a joint travel to be done. And all these different specifications and workflows are arranged by the scheduling part of the backend. And it is automated in a way that if we initiate the sequence of the models, this will run in the background and create the different workflows for each agent. An important innovation of the Harmony MS, the tactical passenger simulator of the Harmony MS, is that it opens a series of specification parameters, like the ones we talked in the previous slide, to the final user of the platform. What does this mean? I'm going to describe a small detail of the workflow, which is the scheduling of an activity right after the primary activity, in case that the time that the model predicts the secondary activity to start is really close to the end of the primary activity. So imagine that we predict start times and travel for two different activities, the work activity and the shopping activity. And the model for a specific agent predicts that the work activity is going to end at 5 p.m. and then the shopping activity is supposed to start at 5:30 p.m. So there's a half an hour break between these two activities. Of course, this does not include at this moment the travel time from work to any other activity. But we know that the time window between the end of the first activity, the work activity, and the start of the next activity is half an hour. If we were in my hometown, the island of Chios in Greece, this time window of 30 minutes is enough to go back home, leave your work stuff, and go to the supermarket to do your shopping activity. If we're located in Athens or another big city, this half an hour is not enough, most of the times for you to get back home. And this way, we want to open to the final user, to the policymaker, to the final user of the Harmony MS, the ability to choose this time window, which is a time window that is enough for someone in the city we're talking about, in the city that we have the implementation of the Harmony MS to is enough to get them back home and then start the new tour from scratch. So this is why we open this input parameter to the user, where it can be specified and we can see how much time do we need until we connect the two activities. So if the final user of the platform says that for this specific application, for example, for the case of touring, a time window of 45 minutes is needed in order to connect the activities. In this case, where the half-hour window is not enough for the agent to get back home, we connect the two activities. So we order the agent to go to the secondary activity right after the first is conducted. We calculate the travel time to the next activity, and then we continue with the scheduling. If the next activity, the shopping activity, was predicted to start 2 hours after the end of the first activity, the destination of the secondary of the first activity becomes home, and then we start a new tour from home to the next activity. This slide presents all the different specifications that we can open to the final user, some of which were already included in the specification of the tactical passenger simulator, and the rest of them are open to be discussed by a potential user of the platform. Finally, after discussing the technical stuff, introducing the activity-based models, and discussing about the data requirements and the models we use to present the results and to estimate the different parameters for the different use cases, we want to see why do we do all this complex modeling. And the truth is that in the Harmony project, we envisage an integration of all the recent novel developments that happen into spatial and transport plans, and have the main objective of improving citizens' well-being and achieve environmental targets. In terms of sustainability, social inclusion, accessibility, these are all goals, both in the high-level policy, in the European Commission targets, but also the project-specific targets, the expected income that Harmony brings after its successful conclusion. And modeling, as we see it in the sector, especially if it is presented in an easy-to-use, user-friendly tool, and focuses on plain language, on translating the tech jargon and the modeling jargon into straightforward results, without sacrificing scientific rigidity, can be a key to translating plans into actions. And this is the bridge from technical work, from modeling, from scientific observation, to actually creating a tool which can support policy decision in an informed, knowledgeable way. The use cases that we model in Harmony are the land use and development of new public transport infrastructure in Turin, where there is a different land use in the functional urban area of Turin, work, health, and university, and also the extension of adding a new metro line and metropolitan rail in the same area. And on top of this use case, we also modeled the mass demand, the remote work and activity schedules, and also we apply a low emission zone in the whole functional urban area in Turin. For the same purposes in Oxfordshire, we model the impact of autonomous demand responsive transit service, the impact of demand and supply interaction in this case, the impact of mass schemes, and also we have outlined the investigation of a crowd shipping use case where the tactical passenger and the tactical freight simulators interact. Finally, before closing on the policy section of this presentation, I wanted to show you this is the interim sketch, the wireframe for the dashboard of the Tactical Passenger Simulator. As I mentioned before, this is the place where the user can specify some of the required inputs of the simulation. For example, they can allocate this time window we've been talking about between the activities. They can indicate whether the simulator would model joint tours or not. Family interactions, maybe choose specific zones to model in the simulation. Include some location-specific attributes. For example, for some cases, the school start time is harmonized across the whole city, so there's no variation. There's no need to predict this type of activity. Another interesting and necessary choices, for example, the output of the simulator, which I forgot to mention, can be either in the traditional form of audio matrices or in detailed agent schedules, depending on the module that will get the output and perform the traffic assignment. Finally, I will be talking really briefly about the integration of the Tactical Passenger Simulator. We get input from the strategic simulators. I use here as an example the LUTI model, but of course we also get significant contribution and variables from the REM and the DFM models. We also use input from the vehicle ownership and mobility tool ownership models developed in the in-between, the strategic and the tactical. And also the remote work, mode choice, and other longer-term models are significant inputs to the simulator. And then we generate the demand in the forms of agent schedules and also in the form of audio matrices. And then there is another feedback loop. I'm not going to get into this a lot with the different calibration loops and the engagement of the demand subshifting models. That is another innovation of the Tactical Passenger Simulator and Harmony. We integrate the Tactical Passenger Simulator using the usual Docker container approach that you have been listening to, and Elias from Mobi has been describing this approach. All the different Harmony components are integrated using this way. The Tactical Passenger Simulator is, I think, the only component that is developed mostly in R language, but is integrated using the same approach. And also is at the moment the only component of the MS that has its own specification input screen, as I described in a couple of slides back. This was the short training session on the Tactical Passenger Simulator of the Harmony MS. This is my email where you can reach me and with questions or anything you want to clarify, or any additions, ideas are more than welcome. In the rest of the presentation, I'm leaving the links that I've talked about before with answers to your questions and the detailed instructions for the exercise. I hope you have a nice day, and happy to answer any questions or any feedback regarding the Tactical Passenger Simulator.
Hello everyone, my name is Dimitris Papelis, and today I will present my work on the modeling and behavioral implications of within-day travel dynamics. Let's imagine of our typical daily traveling. We come up with a pre-day schedule, essentially a chain of activities and trips that we need to perform. However, things don't always come out as planned. There are various exogenous factors that could lead us to deviate from our pre-day plan, whether this is weather conditions or congestion, or even our own faulty perception of anticipated travel times. Especially in a post-pandemic world with increasing remote capabilities, it is apparent that the performed within-day choice can significantly differ from the pre-day plan. This observation is magnified from the emergence of travel recommendation systems, journey planners, Google Maps, and mobility services that give access to live information. Thus, although in traditional transportation research, the focus would be on creating the most realistic and accurate pre-day plans, as for instance in activity-based models, there is a need for integrated modeling frameworks. From a behavioral perspective, this phenomena of adaptation and reevaluation of choices are typically associated with a significant resistance to change. Traditional economics are grounded on the concept of rational expectation, where we assume that the individual is aware and processes the variety of information around her, but switching behavior comes with utility costs, the cost of change, and thus we observe this delay and sluggishness in responses and actions. In recent years, there has been a rising interest in the rational inattention theory, originally developed by Christopher Hitchens. The argument is that individuals rationally choose to make seemingly suboptimal choices due to the cost of acquiring and processing available information. It is bridging concepts from information theory to choice modeling. To explore this phenomenon for the scope of this study, data collection was part of a wider travel survey of the Harmony Research Project and utilized a smartphone-based application, the Mobi app, to track the habitual activity and trip patterns of the participants over the course of 5 days. These RP data were combined with a state adaptation experiment aiming to capture the process of within-day reevaluation and day-to-day learning on specific hypothetical scenarios. The RPSP methodology was applied in the municipalities of Turin and Oxfordshire, which led to the collection of more than 8,000 observations. The methodology selected was discrete choice analysis, where I developed a dynamic hybrid discrete choice model in the BioGEM software. The framework accounts for interpersonal heterogeneity and led to some key behavioral findings. Also, a latent variable was measured through a series of attitudinal statements where I defined the concept of adaptive travelers, which can be described from various sociodemographic characteristics. The real-world impact of the modeling framework is threefold. First of all, such models can be useful for transport planners and authorities for demand prediction when planning interventions that will imbalance the typical transportation network conditions. In addition, knowing the probability of adaptation and the characteristics of adaptive travelers is useful for the personalization of recommendation systems to generate menu sets that are tailored to the traveler's needs. Finally, such models can find practical application in increasing the accuracy and realism of agent-based transport emission simulation software. I would like to conclude with the words of Herbert Simon, one of the fathers of decision-making analysis and bounded rationality. Richness in information means poverty of our attention. Therefore, to utilize this wealth of information and increase our well-being, we need to allocate it efficiently among the available sources. The theory of rational inattention, which is the focus of my final PhD chapter, is an opportunity to include these information constraints and study their implications in travel behavior and transport economics in general. Thank you.